Hello, everyone. So, I'm actually going to be talking about a lesson I've done in my class, and this is going to be covering a standard, which is going to be HSPS2-4, which is the Next Generation Science Standard for Physical Science, which says you're supposed to use mathematical representation of Newton's law and Newton's law of gravitation and Coulomb's law to describe and predict the gravitational electrostatic forces between objects. And what I'm going to do is launch a simple experiment. And this simple experiment is using balloons and your hair. What I like to do with my classes is I like to start with a slide that talks about something we've talked about in previous classes. So looking at two particles, exerting a certain amount of force. The one that's closer is going to exert more force than the particle that's further away. The higher the charge also exerts more force. And this goes into Coulomb's equation, which is the electrical force is equals to KQQ over R squared. And I'll develop that more as we go on. But here's what we're going to be doing. We're going to be looking at balloons. Our experiment is to hang two balloons and measure a couple key pieces of information. So in this one, I kind of put together a little bit of fake information to illustrate what they're going to be using. Because what the students are going to be doing is they're going to create a lab report to test something with this idea. What their objective is to figure out what is the charge of a balloon if you rub that balloon on your hair for a couple seconds. So, students can create a lab report that tests out either how long they rub it on their hair, different types of hair, just whatever they choose to make. But I give them the instructions on how to go about finding this charge. And they can always figure out, alright, what can I do to figure out what has more charge, etc., etc. And to do this, all you need is two simple balloons, some string, and something to hang it on. And I would have a separate lab report on a Google Doc or something like that they can edit freely and create. But this kind of gives them an explanation of how they go about doing this. And this makes a great lesson to talk about for this class. So in this case, I'm going to give a dummy problem, where you have a 0.01 kilogram balloon making half angle of 12 degrees attached to a 0.3 meter long string on both sides. Both balloons have the same charge. What's the charge of the balloon? So here's what we can do. To know about this problem, we can simplify it a little bit by making it only one balloon, because the other balloon will be pretty much identical. So this one's going to look on this side, cut in half on the halfway point. A clever physics trick is to split right down the center and say, hey, since they're symmetrical, we can just multiply by 2, not a problem. So by cutting it in half, we're only looking at half of the complicated problem. And to do so, we can look at this saying, alright, the angle's going to be 12. This is a 0.01 kilogram balloon. Angle's 12. String is 0.3 meters long. And to figure out the charge, Q, we have to do a little bit of math. And to do that math, we have to look at vectors. And just a quick review, vectors are 3D representations, etc., etc. You can cut any vector or any arrow, which represents a force in this case, into two parts, the x and the y component. So every force will have force in the x and a force in the y. And this is something we've developed over the previous semester. This would be the first unit on our first lab report on electrostatic forces, which is what they would come in during the second semester with. So by splitting things into x and y, we can set up SOHCAHTOA to figure out certain forces. So I'm going to skip through this a little bit. We're going to be looking at the triangle that goes up and down like this. So Fy is going to be vertical, Fx is going to be horizontal, and we can look at, hey, if I'm looking at the horizontal force, I'm probably going to be using sine. If I'm looking at the vertical, I'm using cosine. So to break this down, we look at Coulomb's law. F equals KQQ over R squared. To simplify it further, since we know both balloons are going to receive about the same amount of charge, that's something students have to set up, charging both balloons about the same amount on their hair. Q1 equals Q2, so F equals KQ squared over R squared. And because of this, this simplifies this down to a couple things. In physics, the whole goal of this game is to find your charge, your Q. This little guy, this Q, is what you're going to be solving this equation for. And to solve this equation, we have to find two other things, the force and the radius. K is a constant, so that's never going to change, and we know what the value of that is already. And that's going to be something we can work in with our problem later. So we got to figure out what force is and what the radius is. Luckily, with a nice protractor, we can calculate our own angle, and with a ruler, we can figure out our own radius. To find the force, we have to do something a little bit tricky. So let's do some tricky stuff. Let's start with the radius, because we can find the radius by a simple measurement of r. In fact, it's actually a little bit hard, so I discourage kids from using a ruler like this. The only thing you'd use the ruler for is to hang the balloons off the ruler. They can do something smarter. If they can measure the length of this, they can use SOHCAHTOA to figure out what this radius here is. So if opposite equals hypotenuse sine theta, we can say, alright, this is our hypotenuse, we can find our opposite. So x equals L sine theta. In this problem, the case of this problem, 0.3 meter long string, 0.3 sine of 12 gives us 0.06237 meters. So we know that this is about 0.06237 meters long, or move this over, 6 centimeters across. So with a radius of 6 centimeters, we can keep playing with this. So the diameter is going to be double that, so about 12 centimeters. Now, to find the force, we have to think about this in terms of tension. If the tension is the force of the string, electric force is what's pushing it over, away from the other balloon, and gravitational force is going to be pushing it down. We can translate this back into the original triangle, where the x is the only force on the x component, and gravitational force is the only one on the y component, and make a nice right triangle with a tensional force. Because tension has to be equal to both the electric force and gravitational force in this right triangle. And because of that, we can split this up into x and y components and solve the Fg. In this case, this is going to be our y component of the force. So to find Fg, we know that Fg equals mass times the gravitational acceleration constant, which is 9.8 meters per second squared. So in this case, with a 0.01 kilogram balloon, that times 9.8 gives us a gravitational force of 0.098 newtons. With that force, we can calculate the force electric. Since force electric is going to be our x, and force y is going to be the force g, we can use tan, which is opposite, over the adjacent. And we can solve for the opposite by multiplying both sides by a, and we get Fx, or our electrical force, is equal to force gravity tan of 12, which gives us 0.02083 newtons. So now we know how much electrical force we have, we know how far apart those are going to be, we know F equals KQQ over R squared, so now we can solve for Q. And this is something I would have my students do, solve this out on their own. They can figure this out because this is more intended for senior students. With this in mind, with the calculation of Q, by square rooting it, they can figure out exactly the magnitude of the charge they created with their hair. And they should usually get something in the range of like 100 nanocoulombs. But based on how much they rub their hair, etc., how much the balloons push apart, they can get slightly different numbers. But they should begin somewhere in the nanocoulomb range. This allows us to actually calculate what the electrical force or electrical charge of their hair is. This allows the students to really play around with what can they do to change these numbers? What can they do to build their own experiment? How can they contribute to one another and figure out in this classroom what they can do to further their scientific exploration? And this works great with all the things that we work on in the class. It's free open lab creation based on scientific principles through mathematics. This really goes into the NGSS and goes through all the other objectives of meeting the mathematical representation of Coulomb's law and Newton's law, and looking at what you can do to spice up your experiment. So there's a lot of interesting things you can do with this lab. There's a lot of things that they can demonstrate their understanding with this self-created lab report. By going through the scientific method, they can create an interesting piece of scientific literature and also present to the other classmates what they have found to be the most effective or least effective way to create charge. If you have any questions, let me know.